Yeah, thank you to Jenny and Hyann for giving me the chance to present today. As Jenny mentioned, my name is Dillon. I'm a new postdoc at Series at CU Boulder. I got my PhD at Scripps. And today I'm going to be presenting sort of a broad overview on the topics of marine heat waves. Well, I should mention that it's sort of a brief, broad overview of marine heat waves. I'll discuss them generally for a handful of slides, and then I'm also going to discuss sort of the application of these broad ideas to specific sort of case studies of marine heat waves. And that's primarily what my research focus has been over the last about a year now, is on this most recent North Pacific marine heat wave. So I'll present some results from a paper that we've written summarizing that particular event. So just to generally speak about marine heat waves for a minute, I don't know how, I actually don't see the participants list, so I don't know who's here, but I'm just going to assume that nobody has any information about marine heat waves initially. And for those that may be uninitiated to this topic, it sort of came into vogue as a scientific topic as a response to this very extreme series of North Pacific sea surface temperature anomalies that began in the winter of 2013-14 in sort of this offshore Gulf of Alaska mass of warm upper ocean temperatures. And this anomaly quickly earned itself the moniker the Blob. So it all started with the Blob, and this is really what initiated the interest among the scientific community in this topic, because as these anomalies evolved, due to sort of a shift in atmospheric circulation, these anomalies evolved and maintained their magnitude as they sort of spread out throughout the coastline here. If we sort of take points at different sort of centers of action over the course of this thing's lifetime, I should have mentioned here that it began in the winter of 2013-14, but it persisted for a very long time, so almost over a year and a half. But if we take points at centers of action in each stages of this thing's life, you can see that at one point it was the warmest the sea surface temperatures had ever been at these given locations. So this was truly an extreme event, and it got people thinking about this concept of marine heat waves. And the reason why we care about these things is because of their impact on marine ecosystems primarily. If we think of sort of traditionally, we think of atmospheric heat waves and their impact on people. Well, critters are the people of the sea, right? And so marine heat waves can really stress out marine ecosystems. And that as humans and as an economy, we can feel that by massive die-offs in different fisheries. And I should mention that I am not a biologist, so if I say something about biology that is incorrect or just slightly off, please feel free to correct me later on if any biologists are listening. But sort of anecdotally, when this event was evolving, I was just joining Scripps as a PhD student, and we experienced a huge die-off of tuna crabs in San Diego County. So hundreds of thousands of these washed up on the shore. And as I understand it, these tuna crabs want to live on a particular isotherm in the water column. Because they know historically that's where their food is. So when the upper ocean warmed as much as it did, they moved to a different part of the water column where they thought that isotherm was now, and their food didn't move with them. So they just starved to death, and they washed up onto shore here. So this was, for a lot of people, this was a very visceral reminder of what was going on sort of in a large scale sense in the North Pacific. And then the media latched onto this, right? The Blob was sort of this center focus for a very anomalous time throughout the globe's oceans when we had an extreme El Nino occurring during the same time as sort of these North Pacific extreme SST anomalies. So at the time, the whole Pacific was basically on fire, for lack of a better phrase. So there's a lot of anomalous activity going on right now, and it stirred the imaginations of the public, the media, and the scientific community. So it's since this event, we've had sort of a slew of papers and research articles about this topic. I wouldn't say that the oldest paper is as a result of this event, but marine heat waves have been studied for a lot longer than this particular event, but they've become more and more interesting, or more and more, what's the phrase here? They've become more and more in vogue, I guess, since this event. But the most important thing was to first of all land on a definition of how to define these marine heat waves. And this Hobday paper is probably the most well-known way to define a marine heat wave. And they sort of draw on the literature of atmospheric heat waves as sort of inspiration for how to best objectively define when an event is happening. So first of all, they needed it to be anomalous, obviously. It needs to be very warm, but it also needs to be extreme. It needs to be above the 90th percentile for some given reference climatology. That anomaly also needs to be prolonged. And by prolonged, the Hobday paper specifically references lasting for at least 5 days. And we'll talk about this in a little bit more detail, but obviously you can see that this particular event lasted for over 1.5 years. So it's a little bit longer than 5 days in some cases. Also, it needs to be discrete. A marine heat wave has to have a definitive start and a definitive finish. And within their definition of 5 days, they said that you can have a cool gap of 2 or less days as long as it's followed by another series of consecutive warm days. So this is how they sort of dealt with ocean noise, ocean weather, I guess you could call it, for marine heat waves. So this is sort of a schematic representation of their definition. If this is a time series as a function of day of the year of SST, you can see that there can be heat spikes where temperature rises above some threshold value, but it doesn't last there very long. But a marine heat wave can be defined when we have SSTs rising above this threshold for a long enough period of time relative to some climatological, seasonally evolving climatological values. And this reference, this definition is useful. But I would argue, just sort of my own personal opinion, I would argue that it's mostly useful for a certain class of marine heat waves. And this is sort of one of the rubs with marine heat waves, is that they can evolve on time and space scales that are wildly diverse. And so this definition in particular, I think, sort of draws a disconnect between biologically and climatically relevant marine heat waves. And by that, I mean that if we look at sort of the ecosystem impacts of marine heat waves that evolve on sort of these climate timescales, these season to month or monthly to interannual timescales versus daily timescales, which is sort of what Hobday had in the back of his mind when he developed these metrics, the ecosystem impacts are going to be very different depending on what sort of how long these things last and how strong the anomalies are over those timescales. But they are going to have some overlap, obviously. And then also, obviously, if we think about the physical mechanisms that drive marine heat waves on these different timescales, they're going to be wildly different for the most part with a little bit of overlap. So I think outside of this definition, I do think it's important to sort of separate these timescales in your mind from a physical standpoint. But if we think about it biologically, it's also needs to be separated because biology is going to respond differently depending on the time scale and the strength of the anomaly. And I think the best way to sort of summarize at least the physical aspect was done by this Hallbrook et al. Paper in 2019. And I have references for all of these at the end of the slideshow. But basically, if we think about a mixed layer temperature budget, which is the broad definition of how we're going to define these marine heat waves, there's all sorts of things, all sorts of physical mechanisms that can drive variability in the mixed layer temperature budget. And if we think about marine heat waves, the components of the mixed layer temperature budget can be influenced by things on, as I mentioned, all sorts of spatiotemporal scales, ranging from about 10 kilometers to 1,000 kilometers or a day to hundreds of years. And marine heat waves sort of sit right here in this sweet spot, this zone of days to years, or 10 kilometers to about 1,000 kilometers. And there's all sorts of interesting variability that can influence marine heat waves on these different time and space scales. So while the Hobday definition is somewhat limiting for these longer time and larger spatial scales, it is really useful for these sort of daily and smaller spatial scales. So what I'm going to do now is sort of illustrate for you how different various mechanisms that have driven two specific marine heat waves and that people have sort of vetted in the literature on sort of these longer and larger spatial scales. So real quick, Jenny, I think there's chat. There's people are commenting in the chat. I just want to make sure that, okay. Cool. I want to make sure that I wasn't being pinged as if nobody could hear me. I've had that happen before where I'm talking for 20 minutes and I realize that I'm on mute a little bit too late. Anyway, yeah, so let's think about the mechanisms for two specific events. We're going to look at this initial blob that was initially driven in 2013, 2014. Nick Bond and colleagues had shown that this particular event was driven by sort of a prolonged ridging event, atmospheric ridging event that we ended up calling the ridiculously resilient ridge that sat over the Gulf of Alaska for several months. And because of that, it weakens the climatological elution low during this wintertime period, which decreased the amount of power going into the ocean for mixing processes and shoaled the mix layer anomalously. So as a result, you had a smaller mix layer volume, you increase stratification, and you end up warming the upper ocean just through the same sort of surface heat fluxes. And sort of interestingly, Richard Seeger and colleagues then showed later on that this ridge that we saw in observations, at least part of it was maintained or persisted through SST forcing. So this is again going toward those longer time and spatial scales where remote teleconnections from things like the tropical Pacific can reinforce these patterns and generate high latitude anomalies that persist for a long period of time. So they were after this ridge and basically showing that SST forced AGCM experiments can generate a persistent ridge as well that is consistent with what was going on in observations. And so these first two bullet points just sort of summarize what I mentioned, but an important component about this 2013-14 anomaly was that it primarily evolved during the winter time, or at least it was triggered and intensified during the winter time. Winter of 2013-2014, and sort of another emerging theme in marine heat wave research that I've noticed at least is sort of the separation of the seasonal mechanisms that drive marine heat waves and decide whether they will intensify, and when they do intensify, how long they'll last, basically. So if we fast forward about 5 years and we look at a different season and a different event here, we're looking at JJA, summertime of 2019. These are the SST anomalies during this past summer, basically. And so if we take a box average of SST anomalies in this region, this sort of blob region, you can see that these anomalies, not only were they bigger than the 2013-2014 event, but they were also the biggest on record, basically, at least within this region. So this is sort of a resurgence, the return of the blob, a return of these anomalies, but primarily happening in the summer season. So part of my research was focused on trying to understand this particular event and understand sort of the seasonally stratified mechanisms that drove this particular event. So these, for what it's worth, the results that I'm about to summarize are have just been accepted in Nature.com, but there's a preprint on my ResearchGate if you're interested in looking at the details more specifically. But I'll leave you with the take-home points right away, that this blob 2.0 is what we call it, was forced by a weakened atmospheric circulation, similar to the first one, except this time the summertime is dominated by the North Pacific High. And it was maintained by air-sea interactions, and unique air-sea interactions that are unique to the summertime and not the wintertime. But also surprisingly, there was some remote SST forcing, we think, that helped persist this weakened atmospheric state and persist these anomalies over a long period of time. So we can see that, first off, by looking at atmospheric circulation and observations during this time. This is JJA 2019 sea level pressure anomalies. The solid contours here are the climatological North Pacific High. So you can see that the North Pacific High is dominating North Pacific atmospheric circulation. The shading is sea level pressure anomalies. And the colored contours here are the same SST contours that you see over here. So basically what we're seeing is basically a weakening of the North Pacific High in place, and maybe a slight shift southwestward as we have these negative SLP anomalies sitting on top of the high pressure. And also you can see that where the gradient is strongest, the SLP gradient is strongest, that's right where the SST anomalies are following. So if we think about the implied winds around these sea level pressure anomalies, they're going to be strongest where this gradient is strongest, and they are also strongest. I'm sorry, the SST response is strongest where those sea level pressure gradients are strongest. So that sort of implies that on some level, these SST anomalies were generated by wind forcing. And so this weakening of the North Pacific High lasted for a long time. And I'll show you some monthly maps a little bit later, but this was a multi-month weakening of the North Pacific High. And we can quantify how weak the North Pacific high was with respect to the historical record. So the gray line is an index for North Pacific high intensity, with negative values being weaker and positive values being stronger. And you can see that this was, based on this index, it was the weakest the North Pacific high had been in at least the last 40 years. And you can see that the SST, the JJA SST averaged in this box is well correlated with the intensity of the North Pacific high. So this also suggests that this might be a primary driver of summertime SST extremes in this box. So what impact did the change in the atmospheric circulation have on the upper ocean? So we can look at the mixed layer depth, the summertime mixed layer depth from 1980 to 2019. Overall, there's actually a shoaling trend that we'll talk about a little bit later. But if we look at just 2019, you can see that this is the shallowest the mixed layer had been in at least the last 40 years. But if we look at wind speed cubed, which is, again, is sort of a measure of the power imparted by the atmosphere for mixing processes in the upper ocean, you can see that it wasn't the weakest it had been, but it was an extremely reduced strength in the amount of wind stirring going on in the upper ocean. And then obviously these two things are really well interannually correlated as well. So the wind speed cubed can be a strong driver of how deep the mixed layer is going in this part of the world. So we can quantify mixed layer temperature budget to look at what's driving the temperature changes in this box, in this volume, a little bit more quantitatively. So within this box, we have this, we have the August minus May mixed layer temperature tendency, which is blue here. So this is August minus May every year from, I guess I don't have the X-ticks, I'm sorry, but the first dot is 1980 and the last dot is 2019. So this is the August minus May temperature change in 2019. And then this is the temperature budget, the contribution of the heat flux terms to the temperature change, basically, for each of these different terms. So if we look at just the tendency for a second, basically all of the warming that we saw in 2019 was due to warming happening from May to August. May wasn't particularly warm. It was slightly warmer than normal, but it wasn't particularly cold either, where that difference would be really big. It was mostly just warming going into August. If we look at the advection term, we can see that it's really small. Part of the reason for that is because our box is really big. So as we make our volume bigger, things like advection due to eddy mixing, for example, would be reduced. So we can sort of quantify that using eddy kinetic energy during that summertime. You can see that in our volume, there's basically no eddy kinetic, well, there's no strong eddy kinetic energy going on in our volume. So we didn't expect the advection term to be a big driver here. If we look at the heat flux term, I'm not going to break down, just for brevity's sake, I'm not going to break down the individual heat flux terms in all their components, but I will show you the two most relevant terms. The latent heat flux term, this is the evolution of these terms from January of 2019 to August of 2019. This is the temperature increase that we saw in that box. This is the latent heat flux component of that, and the shortwave, the surface shortwave component associated with that warming. And basically, what I wanted to show here is that the mechanisms for triggering this event. So in this case, it looked like we reduced atmospheric circulation, as we saw with the weakening of the North Pacific high. That would reduce evaporative cooling at the surface and give you a downward latent heat flux. So that's what we see here. This is the triggering of the event when we reduce the atmospheric circulation. But later on, when these anomalies were much stronger, the latent heat flux anomaly tanked, and it wasn't as important in maintaining these anomalies. What was more important was the shortwave. So you can see that as the anomalies get warmer and warmer, the orange line gets taller and taller. So the shortwave becomes increasingly more important. And the reason for that is something that's more unique to the summertime. In the summer in the North Pacific, we have really pervasive low clouds, marine stratocumulus clouds. And if we warm the boundary like this, we can burn off these low clouds, which will increase shortwave coming into the surface and increase SST, giving you a positive low cloud SST feedback. And so if we look at MODIS satellite observations of low cloud fractions, you can see that there was a significant reduction in low cloud fraction pretty nicely following the warmest SST anomalies during this time period. So that's what's going on here. As these SST anomalies got bigger, we just burned off more low clouds. But a big take-home point here is that the triggering mechanisms that trigger these events can be different from those for their maintenance. And this is something that A paper by Lauren Schmeiser at the University of Washington recently was published to sort of make this point for the 2013-14 event. And we're also seeing it again for this 2019 event. So just very quickly summarizing the results of sort of this observational analysis. Again, this event was driven by a weakening of the circulation primarily. It was triggered by the weakening of the circulation, which also shallowed the mix layer. And once the mix layer was very shallow, we could distribute stronger surface heat fluxes over a small volume and get such a strong warming during this time period. So I mentioned that this weakening of the North Pacific high was very persistent. It lasted several months. If we look at SLP anomalies from May to October of 2019, you can see basically a persistent low pressure anomaly center, at least through May through August, and to some extent through October. And such a persistent feature like this suggests that on some level there could be SST forcing that sort of helps keep these anomalies in place. So one way that we wanted to test this was by looking at the observed pattern and realizing that observations is the summation of sort of internal variability, random noise, plus potentially some SST forced or deterministic components. So we want to be able to isolate this potentially deterministic SST forced component. So the way that we did that is we ran a series of AGCM experiments using GFDL AM 2.1. We forced our model with global sea surface temperature anomalies, basically this map. So we ran 3 sets of simulations. We forced it with global sea surface temperature anomalies, tropical sea surface temperature anomalies, and North Pacific sea surface temperature anomalies. And in these limited spatial forcing runs, everything else outside of the box of interest is just a seasonal cycle for the boundary condition. So we ran 3 sets of simulations, 20 ensemble members each, and we ran them from January 2018 to August 2019. And we just basically threw away the first 17 months spin up, and we only analyzed June through August of 2019. And so basically the goal was, how well can you reproduce the weakening of the North Pacific high that we saw in observations? Excuse me. If we look at the ensemble mean of the global SST forced experiment, the tropical SST forced experiment, and the North Pacific SST forced experiment, these are the SST, in theory, this is the deterministic forcing from SSTs on the atmosphere. We can see a general weakening of the North Pacific high that is at least spatially consistent with what's going on in observations, if not in magnitude. But we wouldn't necessarily think that the ensemble mean would be able to reproduce the observations magnitude in reality, because in observations, you also have that internal component that can either amplify the signal or obscure it. And in this case, it seems as if internal variability was adding to the magnitude of this anomaly. We can test that by using our ensemble members, which are a combination of random internal variability, just like observations, with the same SST forced deterministic component. So basically what we can do is we can find an ensemble member that looks more like observations based on a pattern correlation and just see if adding some internal noise gives us a better match with observations. So in this case, we have a best member for each set of ensembles where we were able to better capture, I would argue, better capture the spatial structure and magnitude of observations, which sort of suggests that the magnitude of this event was almost certainly due to internal variability, but the spatial consistency sort of suggests that the weakening of the North Pacific high was at least informed in time. It was allowed to persist because of SST forcing on some level as well. And then the last thing that we sort of looked at was we needed to confirm the presence of this low cloud SST feedback. Again, in observations, we saw a reduction in low clouds due to increased SSTs in the real world. And we should be able to see that in our AGCM experiment as well. So we force our AGCM with just North Pacific SSTs. We also see a very similar reduction in low clouds. So this was basically confirmed the presence of low cloud SST feedback during this particular event. And this is, again, something that is more unique to the summertime because of the pervasiveness of low clouds in the summertime. So yeah, just summarizing these model results, the magnitude of the weakened North Pacific high was consistent with internal variability, but remote SST forcing likely contributed to the pattern and persistence of these anomalies. And then again, low cloud SST feedback was almost certainly important in maintaining this particular event. So I just wanted to also just show where we are now, basically with these anomalies. This was summer 2019, and this is now DJF of basically the past 3 months, DJF 2019 to 2020. And you can see the SST anomalies are they're still strong. They shifted slightly closer to the Gulf of Alaska due to changing in atmospheric forcing, but they're still pervasive. Also, the central equatorial Pacific around the date line is also still significantly warm, which I think is interesting as well. I want to make a couple final points. I know I'm close to time here, but I think these are important just for our general understanding of marine heat waves, particularly the role of ocean persistence in maintaining and prolonging these particular events and what it means for marine impacts. This is a cross-section, a Havmuller of temperature with depth in the Northeast Pacific in that same box. And this gray line is a repeating climatological mixed layer depth in this box. And so basically what I wanted to point out is that during the winter of 2013-2014, we initialized this initial Blob 1.0. And what happens is because that happened in a deep mixed layer season, those anomalies were mixed very far down, very far down relative to the depth of the mixed layer. And then as that mixed layer depth began to shoal with the seasons, those mixed layer depth anomalies, this temperature anomalies were trapped below the rising climatological mixed layer depth. And what can happen is that as the mixed layer begins to shoal in the following winter, those anomalies can mix back up to the surface and add to the persistence of these anomalies from year to year. So Blob 1.0, the 2013-14 event, was prolonged because of this ocean reemergence signal, basically. Whereas if we fast forward to 2019, this event was triggered during a shallow mixed layer season. So it just goes and it just sits there. And in the absence of persistent atmospheric forcing, these anomalies would just dissipate. But we've had some persistent atmospheric forcing. So as the mixed layer depth has begun to deepen, these anomalies have also begun to deepen. So it's possible that if these continue to deepen and they're strong, these anomalies could resurface a year from now due to this ocean reemergence mechanism. And so what does this mean for marine impacts? Well, wintertime marine heat waves, those that are triggered during the deep mixed layer season, could potentially have intense but also prolonged impacts on marine ecosystems, whereas summer marine heat waves, without prolonged atmospheric forcing, they could potentially produce intense impacts, but much shorter lived because they'll just dissipate and not have this extra persistence due to ocean reemergence. And then finally, the last thing I want to touch on is what our general understanding of the influence of climate change on marine heat waves. Probably the most well-known paper on this topic is this Fröhlicher paper, where they look at the change in the probability of marine heat wave days due to climate change. And basically what they show is that basically everywhere you increase the tails of the distribution, the likelihood of the tails of the distribution, excuse me, with increasing temperature. And obviously it's going to be strongest where you have the strongest mean SST. So they're basically attributing this to a shift in the mean SST. So you're just basically shifting the distribution towards warmer temperatures. So this is the same argument that people have been making with atmospheric heat waves for decades, but now being applied to the ocean. And then one other topic, one other influence of climate change potentially on marine heat waves is the effect of a shoaled mixed layer depth in the mean due to climate change on the likelihood of an SST signal, basically. So I mentioned that there was this shoaling trend that we can see in observations. And so I'm doing some work right now trying to understand the extent to which this shoaling trend is due to climate change, to the extent to which this is a real shoaling trend. Obviously, we don't have a ton of subsurface observations prior to the Argo era, so there are some questions about the validity of this trend. But just mechanistically, you can understand that this would be important if we just sort of look at the tendency equation for a mixed layer heat budget. If you basically have Q over H, if you decrease H bar by shoaling the mixed layer, you're going to reduce the denominator here. So for the same surface heat flux perturbation in the future, we're going to have a stronger SST response because you're basically mixing the same Q flux over a smaller volume. So this potentially could also sort of shift the distribution of SST extremes due to a shoaling mixed layer. And I'm running out of time, so I won't go into this in a ton of detail. Sort of the cliff notes is that CMIP 5 and CSM, the large ensemble, show a shoaling of the mixed layer in the Northeast Pacific of about 4 meters. And this is primarily due to a change in the buoyancy flux, specifically the heat buoyancy term due to Q fluxes. And if we think about when these forced mixed layer depth changes will emerge above some metric of internal variability, we can talk about a time of emergence of these forced mixed layer depth changes as a function of space. So for the Northeast Pacific, this is thought to emerge in the mid 2030s, maybe mid 2040s, depending on which force component you want to look at, but with a pretty considerable range of about 30 years across the ensemble members. Again, depending on if you look at the large ensemble versus CMIP 5. So I know I rushed through that last part, but I guess I just wanted to impress upon everybody the different ways that people are considering the impacts of climate change on the likelihood and intensity of different marine heat waves. So with that, I will leave a handful of references for you. A couple are mine, and the rest are sort of these other papers that I find really useful when thinking about marine heat waves. And with that, I will take any questions. Thank you.
Great, thank you, Dillon. So if you have any questions, feel free to use the raise your hand button to let us know that you have a question. Otherwise, if you have trouble finding that or with your audio or anything, you can type it into the chat box. So I see that Zool has a question. Go ahead, Zool.
Hey, Dillon, very interesting talk. I have 2 questions about your AGCM simulations. Did you suggest the tropical SST makes the contribution to trigger the North Pacific high anomalies?
Let me just repeat it to make sure I understood your question. Your question was I suggesting that tropical SST anomalies were contributing to the weakened North Pacific high? Was that it?
When you discuss the mechanisms, initially it's like atmospheric circulation anomalies kind of like trigger the SST or the heat wave anomalies. Then you have like positive feedback between low clouds and the radiation. Where does the initial circulation anomaly come from?
Oh, I see what you're saying. Yeah, that's a good question. I think most likely it was due to internal variability, but the SST structure was at least conducive to persisting those anomalies due to large-scale atmospheric teleconnections. At least that's what we're suggesting. Although again, the magnitude was consistent with internal variability. So it's the timing of the weakened North Pacific high was potentially more due to internal variability than that SST forcing.
Okay, so that means the timing is not very predictable.
It can't. I mean, I don't want to make any broad statements about all marine heat waves. I think on this particular instance, potentially the timing is harder to predict than the timing may not be deterministic. But with other marine heat waves, say if they were generated in the wintertime, when INSO teleconnections, for example, are more reliable, then there might be more of a deterministic component in the timing of the event.
Okay. My second question is about the differences between the simulations and the observation. In addition to magnitude differences, we also see like different spatial patterns. Although they are all negative anomalies contributing to the weakening of the North Pacific high. When we have a different spatial pattern, does that have like any impacts or implications for the interaction with low clouds?
Yeah, that's another great question. I guess my first instinct is that the distribution of low clouds in the model is probably not consistent with observations. I mean, there are almost certainly biases in the model for low clouds, as there are for the position of the jet and the position of the North Pacific high. So part of the differences in the spatial distribution of the anomalies could on some level be chalked up to the biases within the model itself. But I think within the modeling framework, the mechanisms have to be physically consistent. So I think that's why we're seeing a reduction in the low clouds in the model consistent with observations.
Okay, thank you.
Yeah.
We have a question from John.
Yeah, hi Dillon, how's it going?
Good. How are you doing, Dr. NG?
Pretty good. That actually wasn't my question, but when you first put those SST time series up for the 3 hotspots for the 2013 to 2015 heat wave, I noticed that the 0 line actually seemed to fit the mean trend of the time series fairly well. So I'm wondering how much of the importance and surprise of the Blob heat wave was associated with the relative absence of SST warming up to that point. And this sort of ties in with the work that your co-authors Kosaka and Shea did on the effect of the large-scale basin SST variations on the global warming hiatus.
Let me, if you don't mind, I'm going to pull up that slide just so I can see exactly what you're referring to. Hopefully this doesn't break. Let's see. Okay, so you're referring to this slide.
Right.
Right, okay, so you're referring to the 0 line here being consistent. Are you referring to this trend, basically?
I'm referring to the 0 line being a very good description of the trend in the SSTs up to the year 2013. And so the absence of warming has sort of made the anomaly be that much more anomalous compared to recent history.
Yeah, that's a good question. Yeah, I don't know. I mean, I don't think anybody, that's a great research question. I don't think anybody has made that connection. The fact that the North Pacific SST trend was ostensibly flat up until this point. And it's unclear whether this blob was sort of a response to sort of the release of that hiatus trend and going back to sort of business as usual. Yeah, I don't know. That's a great research question. I'm not sure.
Thank you.
Okay. And a question from Haiyan.
Dillon, nice job. I cannot help making the connection, the visual connection between the blob and the Pacific meridional mode. Can you tell us a little bit about that?
Yeah. So in this case, the blob as we know it, at least in the literature, is just referring to this pattern. People have since sort of diagnosed the different patterns of SST anomalies that evolved later, and this is a very classic Pacific meridional mode event. So meridional mode events and other climate modes, things like ENSO, can be classified as marine heat waves, which is, again, sort of the limitation of the Hobday definition, because it's not discriminatory of SST anomalies and their relationship to climate modes. So absolutely, like Pacific meridional mode events can inform the spatial structure of a given marine heat wave event. And if we just zoom in on the 2019 event, there is another PMM event going on as well. And see if I can get to that slide. Yeah, this is another positive PMM event. So the reason why the PMM might fire off when anomalies are strong in the Northeast Pacific has a lot to do with the large scale circulation. In this case, we weakened the North Pacific high, and those anomalies dipped down into the trade winds, and the PMM's forcing. Here we go. The anomaly is associated with the weakened North Pacific high, dips down into the trade winds, and the PMM is triggered when you weaken the trade winds. So it's just all connected to this large scale forcing.
Do you see any connections between the exotropics, like see the blob, the warm anomalies associated with the blob penetrating into the tropics? Or
oh, whether they were physically advected, for example, is that what you mean? Diane?
Yes.
Is that what you meant? Were they physically affected?
I just wonder whether these blobs can can penetrate into the tropics and bring predictability to the tropical state, and so or. Yeah,
I think so. A couple papers have looked at sort of Ekman transport associated with that initial blob, and they did show some positive Ekman advection of the blob anomalies to lower latitudes, but it dissipates really pretty quickly. I think to get the anomalies as large scale as they are in the subtropics here, it's mostly due to large-scale atmospheric forcing.
Okay.
That being said, the blob anomalies can absolutely be advected onshore in a meaningful way. So a lot of these anomalies can get pushed around by ocean circulation and then impact critters along the coast, depending on how close they are, basically.
Okay, thank you.
Yeah.
We have a question from Michelle LaRue.
Hi, really nice talk here. Can you go back to that slide where you were showing the SST forced experiments?
Yes. The design of it or the result?
The result to the atmosphere.
Yep.
Yeah, perfect. So it does cross my mind that you're, I believe, forcing this with the pattern that happened. In other words, you already know the SST pattern, and you're looking at the response to that. So it's a bit of a different question, but to what extent was that pattern actually predictable, the SST pattern itself?
That is a good question. I guess it would, since it's pretty clear that the SST pattern was driven by the atmosphere, I guess I would argue that the limitation of predicting the SST pattern itself is limited by our ability to predict the atmospheric circulation. I get that that's kind of circular. It's a bit chicken and egg.
Yes, yeah. No, I just wanted you to mention that.
Yeah, it is a bit chicken and egg. But I guess the point I'm trying to make is that the SST forcing at least has a predictable response depending on where it's coming from. So if we see, I guess the motivation is if we see SST patterns similar to this in the future in the deep tropics or in the subtropical North Pacific, we might expect this atmospheric response as a prediction, excuse me.
Right, but I almost feel like you would know that it happened after the fact. So the question is, what are the initial conditions that actually led to that particular ST pattern, which interacted with the atmosphere?
Yeah, I guess, it's a good question. I mean, you could initialize a model with like April SSTs and see how often you get the same sort of pattern. But I guess in this framework, it's pretty limiting to sort of diagnose that. But I recognize that the pattern itself is informed by the sea level pressure anomalies. But I guess the only argument I would make is that the forcing, the SST forcing that we're testing here is relatively remote from the target, which was the SST pattern in the Northeast Pacific. So the Northeast Pacific SSTs were almost purely a response to the sea level pressure, to the atmospheric anomaly, but they didn't force the atmospheric anomaly. So I guess the remoteness of the pattern is also important too, if that makes sense. So like the tropical Pacific was anomalously warm around the dateline, and that had nothing to do with what was going on in the North Pacific. So that's sort of your initial condition.
Right. Okay. No, thanks so much. I appreciate that.
Yeah.
And can I say something? This is Antonietta, and this also goes back to Jan's question before. I think this structure, like these meridional modes and also this warming in the central kind of Western Pacific seem to be kind of concurrent features in many, which may be all of these features results of the large-scale atmospheric circulation, which then can also teleconnect to the extratropics.
Yeah. Are you referring to the warming around the dateline versus warming in the subtropics?
Exactly. Yeah. So I think while there have been studies that have shown the possibility of this equatorward migration of the meridional modes anomaly through the west feedback, I think oftentimes what we see that this anomaly around the dateline tend to be concurrent also with the anomalies that are associated with the meridional modes. Right. And somehow maybe the results of this large-scale pattern, which, but then in the ocean they tend to persist, and so can, feed back to the atmosphere.
Right. Yeah, it's the PMM and this like Central Pacific INSO and PMM are hard to separate because they're not entirely independent of each other. So yeah, that's also very much an open research question. But as they've, I think their relationship to marine heat waves, at least in the North Pacific, is also sort of another burgeoning topic that people have been thinking about recently as well.
Yeah. Dillon, this again is Antonietta. I also have another question concerning your plot where you were showing the Hofmöller diagram of temperature with depth and mixed layer depth. Yes, this one. So I just have a comment on this. I think clearly when you have during the 2014-15 period, when you have this deepening of the mixed layer in the winter of 2015, that coincides with the intensification of the anomaly at the surface. However, like the reemergence per se would bring weaker anomaly at the surface, because if you look, in fact, how they fade at depth below the mixed layer during the previous summer. So I think concurrent maybe with some reemergence. So the reemergence can only explain a small fraction of the warming that we see in the winter of 2015. So there must be some also re-intensification of the atmospheric forcing to create those large anomalies.
Right. Yeah, absolutely. Yeah, I knew this was going to get me in trouble.
No, it's not trouble. It's just, I think, a clarification.
Is the mixed layer, yes. Dillon? I was curious about this too. But you just have the climatology of the mixed layer depth there. But do you know what the mixed layer depth was at that period of time? Do you know how it relates to the climatology?
Like what the anomaly was?
Well, if you actually drew the actual mixed layer depth in that region. I mean, I agree with Antonetta that if you just take the figure at face value, there's no reemergence here whatsoever. This is the trick with reemergence. In fact, the reemergence signal, when you see it, it doesn't look like this. It's more obviously coming up. So here you have something where the intensification, it's like, the lines are all parallel. So there's no suggestion that it's coming up at all. But there is that signal earlier, and I guess my question is that, do you have the mixed layer depth basically off here because you're showing the climatology and not what was happening that year?
Yeah. So I guess two quick comments on that. I drew this arrow mostly as an illustrative point. I understand that the re-intensification of all of this would require extra atmospheric forcing. Otherwise, you would see a similar resurgence in this winter as well. I guess I would argue that there is at least some reemergence going on here, because you can see these lines are parallel, but earlier on, as the mixed layer is deepening, I think most of the reemergence in this figure is happening in these shoulder seasons as it keeps going down. But that being said, I do have, I wonder if I have it as an extra slide, but I do have the mixed layer depth plotted on top of this plot somewhere, and I'm hoping that it's in my extra slide.
I mean, just while you look at that, if you look at the figure, a reemergence, the kind of thing that you see with reemergence is what you see the following year, right? So as it's deepening going into 2016, that's where you see kind of a subsurface anomaly, which is obviously getting mixed into the mixed layer as it's deepening. But what you're seeing in the year before looks nothing like that, really.
Okay.
I also want to remind you that, like, in the winter of 2015, there's still a strong ridge over California, and this could be another wind-forced warming signal.
Right. Yeah. So I think it's a combination. Yeah.
Right. I would agree with that. Again, I knew as I made those arrows, I knew it was going to get me in trouble. Let me. I do have it in a separate presentation, and I think it's worth pulling up. So I'm just going to pull up the mixed layer depth for that particular figure. Loading. I think it's this slide 26. Here we go. So this isn't exactly the mixed layer depth. It's the anomaly fraction. So it's the fraction of climatology over this time period. Is this helpful?
So if we read this correctly, it's basically saying that the mixed layer was considerably deeper for that period of time. Is that a fair? It's kind of a
shallower. It's negative. It's negative in this case. So that's
not the depth. That's the anomaly. I see.
It's the anomaly, right? So this is the fraction of the climatology. So it was about 20% shallower than the climatology when the 2013-14 winter happened. And then in this case, it was something like 25 to 30% shallower than the climatology.
Right. Then it looks even less likely that it's reemergence and more like it's all atmospheric forcing, right? Because then imagine that black line being higher than it is. There's no, it's totally cut off from any subsurface anomaly. There's not much subsurface anomaly to speak of. Fair
enough. Okay, I guess I included this to sort of make the point that it's possible. So for this particular event, maybe it's not the case, but I think that obviously ocean reemergence is important in North Pacific Ocean dynamics, and it could persist marine heat waves as a concept, maybe not this particular event, but yeah, it's important for illustrative purposes for the sake of the webinar.
Yeah. And I guess it's something that we need to understand more. That's
sure.
And we have a question from Andy, who's been waiting patiently. Andy, go ahead with your question.
Oh, thanks. Yeah, just listening to the discussion with Michelle earlier, it strikes me that we're probably still in a phase in our understanding of the marine heat waves, which would make it difficult to say anything really concrete about predictability at different lead times. Is that correct? And I guess if so, I wonder if you could comment on, what we need to understand better to get to a point where we can perhaps predict marine heat waves on different timescales, whether subseasonal or multi-year or even decadal.
Yeah, that's a good question. I think the biggest difference will obviously be spatial scale. I think we potentially may have made better inroads at marine heat waves that are more coastally located, maybe within tens to 100 kilometers from the coastline, maybe more so than these large scale marine heat waves that have been more the focus of my work. As to what we could potentially do to increase the predictability of these, I think a lot of it has to do with our understanding of the deterministic component coming from like SST forcing. I mean, otherwise they're completely randomly generated, but once they are randomly generated by the atmosphere, also in sort of increasing our understanding of how these anomalies are being moved about, either through, as we've talked about, ocean reemergence, or I guess also even lateral ocean reemergence, not just the sort of in place, but also sort of subducting anomalies below the mixed layer in one spot and then watching them resurface in another spot 100 kilometers away or whatever. So I think there's a lot of work to be done in the ocean's role in sort of persisting these for a long period of time. And historically, there's been a lot of work on North Pacific Ocean circulation and its impact on SSTs, but I don't think there's been as much work on the ocean's role in maintaining these extremes over a long period of time.
Oh, thanks.
All right, so we're approaching the hour. Do we have any final question for Dillon? And so I don't see any movement on the chat or in the raise your hand area. So with that, so thank you, Dillon, for your presentation, and we appreciate the time you took in preparing this talk, and we are really looking forward to your contribution as the new PPAI panel member. A recording of this webinar will be available on our YouTube channel either this week or next, and I'll share a link once it's uploaded. So this webinar series will continue on the third Wednesday of every month at 2 p.m. Eastern Time, with our next one scheduled for May 20th. Hyan is also leading the organization of that webinar, which will feature Mike Jaycox on our continued theme of marine heat waves. So with that, thank you everyone for joining.